last class, we learned a few concepts. At first we saw what are vector spaces, some examples of them, and then what are subspaces, spans, and linear independence. Now, if any of you in the class are not familiar with any of these concepts, please raise your hands without any hesitation. And if you not say anything, I will assume that you are familiar with these concepts. Okay. So I hope it's exact for all of you. Unless you ask your questions, I have no other mechanism to fathom your understanding. Okay. Excuse me. Yeah. You. What is the span?
The sets of linear combination of, if you are given a set B that contains vectors in it,
yes,
then the span of B will be the set of vectors that are the linear combinations of the vectors in B.
Very good. What's your name?
Part.
Okay. Yeah. So indeed, a span is a set of, well, let's take it this way. If you are given a finite set, it's a set of all linear combinations. If you are given an infinite set, it's a set of all finite linear combinations. Okay. So set of all finite linear combinations of a given set of vectors. Then you by the side of part, excuse me, what's your name? Igla. What is linear independence?
So, if we take a linear combination of vectors and we set the linear combination equal to 0, then it's required that all constants in the linear combination are also equal to 0.
Okay. Alright, thank you. Yes, indeed. Linear independence for humans, it might be interpreted as our independence from the lines which separate us. Whereas for vectors, we have simple. So, two vectors, V and W, are said to be linearly independent if they are not on the same line passing through the origin. Okay. That means, suppose this is our R2, and for example, take this vector V as say 1, 0, and W as 0, 1. Of course, they are not on the same line passing through the origin. Okay, they are linearly independent. Whereas if you take some other vectors, say V dash and W dash, at this point, okay, and this point, so the V dash is some AB and W dash is some CD, such that CD is just some scalar multiple of AB. Okay. So for example, this is AB, say this is 2 times A, 2A and 2B, the columns. That will not be linearly independent because AB and 2A, 2B or minus A minus B will all be on the same line, okay? Or any multiple of this. Okay. So these kind of things are not linearly independent; they are linearly dependent. Okay. So yeah, and we just saw that what we mean by two vectors being linearly independent. Can we generalize this to three vectors? Yes? Yeah? Somebody just mentioned something like that. Yeah.
They should not be in the same plane continually.
Very good. What's your name? Zinel. Yeah. So, yeah, indeed. I mean, here what we saw as a line, that is all multiples of this vector, say V dash. We have such a name for this, right? All multiples of this CV such that C is in the defining field. It's called what? This thing, all the points. Very good. Yeah, this is called the span of V dash. Okay. So span of a single vector is always a line passing through the origin. Okay. Whereas now, what you mean by a plane should be what? Then span of two vectors. Okay. For example, V1, V2, V3 is a linear independent set. If the first thing is that none of them is 0, V1, Vi is equal to 0 for all I, 1, 2, and 3. The second is that V2 is not in the span of V1, and the third condition is that V3 is not in the span of V1 and V2. Okay? Note that this order is arbitrary. I mean, because this is an unordered set. So we will work with ordered sets. Okay? But till now we are just working with unordered set because C1, V1 plus C2, V2 plus C3, V3, the span of this V1, V2 and V3, this is the set of this, where Ci are in the field F on which the vector space containing this V1, V2, V3 are defined, is defined. So what I want to say here is that this order, that these are non-zero, that should be true for all of them, and then that V2 is not in the span of V1 and V3 is not in the span of V1, V2. This order is arbitrary. You would write that V1 is not in the span of V2, and then V3 is not in the okay. V1 is not in the span of V3, and V2 is not in the span of V1 and V3. Okay. So you can jumble up the order and use these axioms in any order that you wish to apply them one after another. Okay. But this will ensure that your set is linearly independent. Yes.
Sir, what if we take infinite linear combinations?
By span of a set, you will always mean that you are picking only finitely many elements at a time and taking their linear combinations. Or you can think of that, you think of this like you're taking all the linear combinations, but only finitely many of them are allowed to be non-zero. Okay, finitely many coefficients are allowed to be non-zero at time. Okay. So now well, the first thing is that an example of a subspace. We get lots of examples of vector spaces, also subspaces, but I'm not sure whether you have seen this in your tutorial. Even if you have seen it, perhaps you can still recall how it went. So given a subset S in V is span of S subspace of V. Yeah. So please answer. S is some subset of V, and you are considering span of S. Okay. The question is whether it's a subspace of V or not.
V is
some vector space. Some vector space over some field.
yeah, it should be.
Why?
Because
So to show a subspace, what do you have to show?
The linear combination of
Yes.
the vectors lying in the vector space.
Right. Yes. And then
and
And what is span? What are the elements in the span?
elements in the span. Yeah, the linear combinations.
Right.
So-
So linear combination of linear combinations is again a linear combination. Okay? So it's closed under linear combinations. Answer yes, because linear combination of linear combinations is a linear combination again. Okay? And then span S is a set of all linear combinations, all finite linear combinations of. Okay, I should write finite linear combination of finite linear combinations is again a finite linear combination. Finite linear combinations is a finite linear combinations. Finite linear combinations. Okay. But before we leave behind the notion of infinite spanning sets, can you give me an example of this? That is a set. Well, at first, what is a spanning set? I found define that first. Spanning set or generating set. I mean, spanning set is of course not equal to a set of spanners. It's not a set of spanners. It's a spanning set is just a set of vectors that spans the ambient space. So, for example, if you are considering a vector space V, then it's a subset of V whose vectors are spanning the entire set V. A set of vectors that spans a set of. Okay, wait a minute. I need to clear the left part. Is this workable? Right part. Excuse me. For you, the left part. For me, for you, the right part as well. No. Yeah. So a generating set is a set of vectors V in Di in V that spans V. Here V is a vector space and a set of vectors, a set S of vectors. Right? Okay, wait a minute, I'll write it again. Okay? A set S of V1, V2, etc. Could be finite, could be infinite. Okay? A set S in V that spans V. That is, you get every element in V as a finite linear combination of the elements in S. Now, the question was that, I mean, henceforth we will consider only finite spanning sets, but before we leave completely, I mean, leave the infinite spanning set behind, we would like to have an example of an infinite spanning set and a vector space V which has an infinite spanning set.
Polynomials.
Polynomials, very good. And what is a spanning set?
1x squared.
Very good, yes. So P, let this be the set of polynomials. Say with some coefficients from F. Coefficients from some field F. Okay? And then consider this set S, which is 1, say x to be the variable of this polynomial. So x1, x squared, etc. from xn, and it goes on. Okay? So every polynomial is a finite linear combination of this with coefficients from F. So indeed, it's a very good example. Thank you, Snehal.
Sir, I have a doubt.
Yes.
So actually, from this statement, what I got confused is, did you mean basis?
Aren't these bases?
No, I haven't yet defined what is the basis.
So a set S of vectors that spans V.
Spans means that you can write any element of V as a linear combination of V.
So that's what bases are.
What? As I said, I have not defined basis. So if you have read something beforehand, read it carefully. Okay. We define basis in this class. Yeah.
So the way you wrote a spanning set by numbering it, does it imply that it has to be at most countable?
Which one?
The spanning set S, does it have to be at most countable?
Spanning set.
Because you have numbered it.
Yeah, I have numbered it, but it's not necessary. So we just took this, but indeed you could write that this is some V lambda with lambda in lambda with whatever indexing set. By the way, that was quite a good question. What is the name again? Amor. So only we quote a bit to see what it will be. Okay? And so after spanning set, we must define what is the finite dimension vector space. So what do you think? The set of polynomials, is it a finite dimension vector space or not? Set of polynomials. So we have not defined again what is the concept of dimension. So let's write it down first. Finite dimensional vector space. Vector space V with finite spanning sets. So we're talking about dimensions, but nevertheless, still we have not defined what is dimension of a vector space or what is basis. We're just saying that if a vector space has a finite spanning set, we'll call that a finite dimensional vector space. For example, now you can say whether the set of polynomials is a finite dimensional vector space or not. What do you? It is? Think again. The set of polynomials, it is spanned by this thing, right? Now suppose it has some finite basis, sorry, some finite spanning set. Forget about this set that Snever mentioned, 1 etc. This finite set. Suppose it has some finite set, finite spanning set. Okay. Then each of the elements in this set has some degree, okay, and one of them has a maximum degree. Well, maybe the maximum is attained by more than one variable, more than one of the elements, but still there is a maximum of the degrees. Right? So now, if you take some polynomial of a higher degree, you cannot express it as a linear combination of this. So therefore, the set of polynomials cannot have a finite spanning set. Okay. So this is this, and let's immediately define what is our basis. Our basis is a linearly independent ordered spanning set of a given vector space. Well, that's implied. Okay. Let's write down a vector space. So it's not just a spanning set, you also need the criteria of linear independence. Okay. By the way, I thought of discussing at least one or two more examples of subspaces. So, and that's quite relevant. So, keep these definitions with us. That is, what is a spanning set, what is a finite dimensional vector space, what's the basis. Let's go back once and see one more example of a subspace, and then we'll come back again. An ordering on a? No, it's a linearly independent ordered spanning set. So that means we wrote here something like V1, V2, V3, and somebody asked whether it's countable, right? So we were like enumerating them, and now instead of, so basically we write a spanning set like this. I mean, suppose we have a countable spanning set or a finite spanning set. Till now we use this notation, right? Henceforth, for denoting a basis, we will often denote it by Blackboard V, and then instead of second brackets, we will use first brackets. So that means the people we are considering, well, V1, V2, V2 dot Vn, or Vn minus 1 dot V1, they all span the same space. Okay? But on the other hand, if we keep the ordering of the basis, and we keep track of the ordering, so we are going to consider maps from spaces to spaces. And these maps will have connection with matrices. Now, if the ordering is changed, those matrices will change. So that's why, whenever we are talking about bases, we'll take them to be ordered. So, an ordered set which spans P, and also all the things inside this are linearly independent.
So it's like we can make our own ordering.
Or
is it a well-defined way to make an ordering?
What do you mean? It's a finite set. So you can, with whatever ordering you begin, do not alter it in the middle of the thing. The matrix representations of the linear transformations will not be unique unless you fix the ordering of the basis. Otherwise, with respect to the, if you call this and Vn minus 1 switched the same basis, the matrix representation of the transformation will not be unique with respect to that basis. Okay, so that's ordering. That means we are just considering the vectors in some particular order, and we are keeping it fixed throughout the problem that we are doing. Okay. Now, yeah, we were talking about an example of a subspace. Okay. So this example we also saw in the earlier class, but a little more explicitly this time. We were considering things like this. That is the null space of some matrix A. A is given to you. Say A is to be a real simple matrix. Consider 1, 1, 1. Okay. All ones. Okay. So this is a 1 cross 3, right? And you're considering all these elements X in R3 such that Ax is equal to 0. So you're looking at the null space of this 1 cross 3 matrix. Okay. Call this W maybe. And what we are now, what we are going to show, well, we are not going to show anything because we already have seen that this is, null space is a subspace. Okay. Null space of any matrix in cross n is a subspace of Rn, right? what we are now going to do is to figure out a spanning set maybe of this space. Yeah. So what does it mean? Ax equal to 0, say x is, consider this as x, y, z, okay? And then Ax equal to 0, not the same x maybe, sorry, x, y, z, and then Ax equal to 0 would be equivalent to saying that x plus y plus z is equal to 0, right? So we are looking at tuples x, y, z such that the sum is equal to 0. Okay. Okay. And now we would like to see what kind of things span this space. So since we have x plus y plus z equal to 0, that means you could replace z with minus x minus y, right? Alright? So put it back there. So this one is then is the set of the tuples x, y, z. Well, z you just replace with this one. So x, y minus x minus y, right? That is equal to x times 1, 0, minus 1 plus y times 0, 1, minus 1. Right? So what do you see? That these two things are indeed spanning your null space. Null space of the factors. So that's the thing I want to talk about. Ah, sorry, this was the last word. So here we just wrote that. Okay, I should have this. Yeah, null space of the in-person. Okay. And if there should any other conclusion be made about this elements of the spanning set, please do it yourself. Okay. We gave some definitions here in our. Okay, so till now we have seen, at least in the definitions of what is a finite dimensional vector space, a basis, and what more? A spanning set. Yeah. Now we are going to have some small propositions. Let's keep the definitions for a while, because while you are writing the proposition, you may refer back to the definitions as well. So we use this space for the first proposition. And I'm going to wipe it out if we need more space for the proof. So proposition 1. An ordered set B okay, because we said that henceforth we are going to consider everything finite, let it be finite ordered set. A finite ordered set B is a basis of B if and only if every vector in V is a vector space that we are talking about, is expressible as a unique linear combination B. So in this formation, spanning set was nowhere necessary. We could have applied that. We just required what is the definition of a basis. Yeah, that's all. Now, which way should we proceed? This is an easy proposition. Perhaps you can tell me the proof. Yeah. So let's first go from every vector B is expressed as a linear combination of the elements of B. So suppose every vector in V is expressible as a linear. So we start from this one and go back. Okay. Let's put a minute. Suppose if V is always vector in V is a unique is given by unique linear combination of the elements of V. Show that this is a basis. Yes, Manoj.
Sir, I was thinking of to go to the next point from the first point. Just a small idea, like say, if you consider, let us say that there is no unique set and two
Yes.
two spans
Yes.
can be corresponding to one vector.
Yes.
Then I can make them equal.
Yes.
Transpose, and then again claim that as they are linearly independent.
What does it mean by transpose?
I mean, take it towards the left.
Okay.
And the coefficients will get, I mean, C1 minus C2 plus
Yes.
Ci.
So you are getting a linear combination.
So
Yes.
that equals to 0 now, as it is linearly independent.
Yes.
Each coefficient has to be 0.
Right.
So the C.
So it's a unique expression.
Yeah, unique.
Perfect. Yes. Okay. Now the opposite way, please. So that is perfect. Okay. I will write it down here. The argument you just gave, but that is for the reverse direction, right? Now we go
First to second.
first to second. Yes. Now we are going from second to first. So how we go from second to first?
I think by definition it is base already a generating set.
It's already a generating set.
Yeah,
So
to
B
linear
is okay. B spans V by definition. Yes, right. The definition of B, and then what you have to show more?
To show that the elements of V are linearly independent.
Right. And what does that mean?
To prove that each vector in V is a unique linear combination, we can just do contradiction.
Not each vector in V is a unique linear
Each
combination.
vector in V is a unique linear combination of the elements in V.
Each vector in V is a unique linear combination of the
We
elements
have
in V.
to now prove that every vector is unique linear combination, right?
No. Now we are assuming that every vector is given by a unique linear combination. We are trying to show that V is a basis. So by definition, V spans V because every vector is expressible as some linear combination of V. Moreover, that expression is unique. So now it's a spanning set. It spans V, right? So what we have to show in order for this to be a basis? Linear independence. Yeah. How do we show that?
We can assume that by combination, if they are not
The
linearly.
expression is unique, so suppose C1 V1 dot Cn Vn equal to 0, so we can write this as 0 times V1 plus 0.
Perfect. That's the answer. Thank you. Yes, it was the same argument?
Yes, sir.
So indeed, since every vector it could be written uniquely, in particular we have that 0 times V1 plus whatever plus 0 times Vn is equal to 0. this is some expression for 0, right? And then what it says that this is the unique expression for 0. So there is no other expression, other linear combination which is giving 0. That's the definition of linear independence, right? So indeed, this is unique representation of 0 as a linear combination of the elements of V. Okay. So that implies the set V is linearly independent. Okay. So it's spanning V, it is linearly independent, and therefore that implies V is indeed a basis of V. Okay. And the converse is the argument that Monideep already gave. Conversely, suppose V is a basis of V, and moreover, okay, let a vector V have two distinct representations as linear combinations of the elements of V. That means you have A1 V1 plus an Vn, V1 to Vn elements of V. V was just V1 Vn. That is equal to some V1 V1 plus Vn Vn. Okay. Two distinct expressions. Now that will mean that, can you work this part out, the middle part? Okay, so that will mean that A1 minus B1 V1 plus An minus Bn Vn is equal to 0, right? And we had that V is a basis. That means the elements are linearly independent. Okay. So that is now, since V is a basis, V1 Vn are linearly independent, right? And that implies A1 minus B1 A minus Bn, that is all the coefficients, are equal to 0. So that is Ai is equal to Bi for all I in 1, 2, 2. Okay. So all the coefficients are, all the corresponding coefficients are equal, and therefore these two representations are not distinct, but they are the same representations. So this is a contradiction because we assume the expression to be distinct. With this, then we finish today's class. In the next class, we begin with linear. Yeah, we actually begin with the relation between spanning sets and linear elements. We go into the definitions of basis and define what is a dimension.